Can you hear me, Tom?
Yes, Brian. Nice that you could join us.
Yeah,
so the connection seems to be good, and you're going to speak to us today specifically about aluminum treatments. And the topic is aluminum treatment for internal phosphorus load reduction and lake restoration. What works, what doesn't, and why. So I think you can take it from here, Brian, and tell us all about this. Thank you very much.
Great, thank you. Well, as Tom said, my name is Brian, and I am a docent or associate professor at the Swedish University of Agricultural Sciences in the Department of Aquatic Sciences and Assessment. And today I'm going to be talking about aluminum treatment. What works, what doesn't, and why. So, as many of us know, aluminum has been used for quite a long time, well over 50 years now, to reduce phosphorus release from sediment. The first reported lake treated was in Sweden and Långskärn, and that was 1968. However, we're looking at probably thousands of water bodies treated. Many of these aren't reported. In Minnesota, where I come from, there's at least a couple hundred, many of them being small ponds that there's just no documentation. Aluminum has been used to drink or treat drinking water for well over 200 years. And why do we use aluminum? Well, the main reason is there's excess phosphorus in sediment, mobile phosphorus that can be released to the water column. Iron and calcium can be used, and they work in certain situations, but they do have limitations. So does aluminum in some situations. And aluminum forms a natural mineral, gibbsite, which we've already heard. That's found in soil and sediment, where it binds with phosphorus. So aluminum is the most common metal in the Earth's crust. We eat a good portion every day. It's found in antacids, baking powder, deodorant, among other things, even though it says no aluminum chlorohydrate here. If you look on the back in the ingredients, it says alum, which is, of course, aluminum sulfate. So I've actually used that one before, but not having anything to do with aluminum. It doesn't bioaccumulate. It's often called a chemical treatment. Our session today is called chemical treatment or chemical treatments, but it's actually a mineral treatment. As soon as you add aluminum to the water, independent of what form it was originally in, you can add it as a rock or a hard mineral, but it forms an amorphous mineral directly after addition. And this mineral begins to crystallize into something called gibbsite, which you've just seen, I believe. And here's just a picture of gibbsite. I stole it from Rob Levinsky. So how does the treatment actually work? And I guess basically what we're trying to do here is just restore the balance between phosphorus-binding minerals and the amount of phosphorus in the sediment. Oops, what is there? So here we have a lake in a natural state. The binding capacity within the sediment prevents release of phosphorus, although you do get some release during summer in temperate lakes, most often. Here we have an affected lake. Excess external loading has led to an increase in internal loading because the binding capacity is too low to keep that phosphorus bound in the sediment. Of course, there are other factors like redox and things like that that occur that change the conditions in the sediment and water. But what we're doing with aluminum treatment here is restoring that balance between phosphorus-binding minerals and phosphorus in the sediment to reduce internal phosphorus loading or release of phosphorus from the sediment. So, what affects longevity? We've seen longevity, that is how long the positive effects of treatment. This has varied from weeks to over a century modeled or longer. There's three main factors: dosing method, lake residence time, and magnitude of external loading reduction, which I will talk about in a bit. And longevity is quite a strange word to use here, I think. If external loading is reduced to a natural longevity or a natural level, longevity is infinite. And this is true for any method with respect to sediment phosphorus release. But of course, in many cases, external loading is not reduced to a natural background level. But even when longevity is short, phosphorus stays bound to that aluminum mineral and eventually gets buried with new sediment over time. So even though I say longevity is not a word that should really be used, now I'm going to use it a whole lot through the rest of my presentation. So to talk about dose here, we did a study. This was in a lake in Thailand where we compared a bunch of different dosing methods here. So I have a table here on the left, different methods and kind of a short description. The first column shows the ratio of aluminum to mobile phosphorus in the sediment, that phosphorus that can be released to the water column, and then the actual dose in grams per meter squared. The top three are all lab assays, which definitely overestimate the amount of aluminum you need. And this has to do with Le Chatelier's principle, A plus B equals AB, B being phosphorus. The less B you have, the harder it is to form AB. It's just harder for the aluminum to find the phosphorus, to put it simply. And so we limit, when we do these things in the lab, we're limiting phosphorus availability. We just have what's in that specific sample, so we overestimate the amount that's needed without getting into too much detail. I only have 15 minutes. On the other end of the spectrum, we have the first dosing method, which was based on alkalinity. Nothing to do with phosphorus, but good not to drop the pH too low. But we have over an order of magnitude difference between these two. So what we found in this study was that a fixed, it should say, weight ratio of 11 to 1, 11 aluminums to 1 phosphorus, was the best to use. And this is because this is a reasonable ratio that we've seen before. And I'm going to show you how you can actually predict binding efficiency. But then this also incorporates a factor of safety, so you don't underdose. But it's a huge range there. And I could see that there's still confusion about how to calculate a dose. And of course, we also use the model a geochemical model to estimate pH change. And there we had to split this dose into smaller treatments of 20 grams per meter squared to keep the pH. It was a shallow system, so not a lot of lake water and thus not a lot of alkalinity available. And here's the big study we looked at. It's getting a little bit old now, published in 2016, where we looked at over 100 lakes that were treated with aluminum. And we're actually able to come up with a longevity prediction equation. And here on the left, I'm showing longevity measured on the y-axis and predicted on the x. It's a log scale, but I threw the actual years down. And we can predict longevity just based on aluminum dose, Osgood index, which is lake morphology, and watershed to lake area ratio. And this includes both residence time and external loading, its relationship to internal loading. A higher watershed area will, of course, mean a larger portion of external loading affecting lake water quality relative to internal loading. However, these dark triangles, the upside down dark triangles, these lakes all have moderate to high densities of carp, and they had shorter than expected longevity due to benthic fish feeding activity. Benthic feeding fish cause an increase in sediment mixing, or the amount of sediment, phosphorus, that can reach the water column. They do have a positive effect on binding efficiency. It helps the aluminum mineral find that phosphorus before it crystallizes too much and loses absorption sites, but it's a net negative effect. So we did a little study on this to measure this. Here we treated Coleman Lake with aluminum. The thatched little ovals here show where we had exclosures to keep the carp out. The rest of the lake was open. The whole thing was treated, exclosures went in, and then we tested the sediment after about 150 days after treatment. And sediment aluminum penetration increased by threefold. And it was really a moderate density of common carp, but they were large, 3.4 kilograms. So in this figure, I show sediment mixing depth on the y-axis here, and you can see the exclosures, the red dot here, we're at about 5 centimeters almost, and that's where carp were not allowed to mix. The three other areas open to carp mixing. You can see the mixed sediment mixing depth, or the aluminum was pushed deeper into the sediment due to feeding activity. We actually dosed based on a 6 centimeter sediment depth. We didn't know this. This study was done after we calculated the dose. We would have been fine if there were no carp. But the carp led to a doubling, at least, of the amount of phosphorus available. So here I'm showing cumulative phosphorus mass in the sediment at 6 centimeters, and then all the way down to 14 centimeters. So that treatment is going to have a shorter than expected longevity. There's another aspect to look at here, and this is the binding efficiency of aluminum after you add it to the lake. So it decreases when greater doses are added to lakes with steep sediment bed slopes, and binding efficiency has varied from 2 to about 20 to 1 by weight. Or I think that's molar, actually. Sorry, but by weight is pretty close. That's a big difference. And so the figure on the left here I'm showing is this ratio, aluminum to aluminum-bound phosphorus, and then the percent recovery. So how much of the aluminum dose did we actually find at these different spots? Because some of these lakes were actually cored into different areas. And what we show here is shallow, flat bottom areas have a lower ratio. They also have a lower aluminum recovery because that aluminum moved into deeper areas of some of these lakes or the deep hole in these deeper lakes. So the more concentration of that aluminum mineral you get, the harder it is for phosphorus to get in there and find those absorption sites. The aluminum crystallizes and binding efficiency decreases because the amount of absorption sites decrease. But they model this now, so we can actually pick what kind of binding efficiency we want, although, I mean, realistically, you're not looking at picking anything less than 5. But yeah, so we came up with a model that predicts binding efficiency using a depth index representing bed slope and aluminum dose. And basically, what we do is to split doses to improve binding efficiency. We also did this in Sweden. This was Oskar Agstam Norlin. He's going to be giving a poster presentation later. This is a little bit different. So here in Sweden, we also use sediment injection, both water application and sediment application. So sediment application, the aluminum is mixed with lake water and injected as at a chosen depth range. So you can hit that phosphorus much faster. At least that's what we assume. It does improve binding efficiency in lakes with steeper bed slopes. So here I'm showing this ratio, again, aluminum to phosphorus, aluminum-bound phosphorus. The lower the ratio, the better the binding efficiency. It takes less aluminum to bind phosphorus. The lighter circles are where water treatment was used, and the ones 2 circled here, these are deeper, steeper sediment bed slope lakes. And you can see water treatment, the binding efficiency was quite poor, whereas it improved drastically with sediment treatment. Not so much effect in shallow lakes, maybe even a negative effect, but I don't understand how that would happen. And binding efficiency, now this hasn't been shown before. We didn't show it in the old study, but now Oskar has shown this, and that's what he's going to talk about in his poster later, mostly. So this is important and affects longevity of treatment. And sediment treatment improves efficiency, at least in these steep bed slope lakes where the aluminum mineral could float across the surface if you do a water treatment. And it also showed the same thing as the previous study. Split smaller doses also improve binding efficiency. Quick case study, Lahti in Sweden treated with aluminum in 2000 based on mobile sediment phosphorus. A sediment treatment method was used with precipitation in the water column. We had sharp declines in phosphorus, chlorophyll A. Here we have concentration, phosphorus in the dark circles, chlorophyll A in the open white circles, and then Secchi depth here on top in the squares. And here's something interesting. Here's phosphorus in the water column, the entire water column. Here's pretreatment on the left. You can see phosphorus reaches over 600 micrograms per liter after treatment. It's well controlled, and it's still being controlled. And there really is no deterioration in treatment effects. There's some variability from year to year, of course, but why do we see this good effect here? Well, an adequate dose was added based on mobile sediment P. Binding efficiency was as predicted. External loading was reduced, which is probably a most important factor here. And now a quick less than optimal case. Cedar Lake, treated in 1996. Here's phosphorus in the black. I'll just focus on that. By 2013, we're not statistically different than pre-treatment. So a 7-year longevity. So what happened? Internal loading returned due to excess external loading of phosphorus. And I should mention a wetland was installed here just prior to aluminum treatment, which often happens. It's very hard to separate these treatment factors. I can't get into that either, but I will talk about the wetland. Here I'm showing the phosphorus in the bottom water. Phosphorus concentration here on the y-axis and days from April 15th on the x. Pre-treatment, the black circles up on top, you can see phosphorus reaches 400 micrograms per liter. The first 5 years after treatment, very little increase, but some. The next 5 years, we have more. And then the last 7 years of data is not significantly, the slope is not significantly different than pre-treatment. So wetland, the Cedar Meadows wetland actually reduced external loading by 50% if you only look at the treated water. The bypass, which was quite a bit, was not analyzed. So the external loading there from that source was less than 50% probably reduced. Other watershed sources, including this one, were still elevated, but also the aluminum dosing method was an old one And there's still, even after treatment, there is quite a bit of mobile phosphorus left in the sediment. So that migrates towards the surface, the aluminum becomes saturated, and internal loading comes back because of that too. So when should we avoid aluminum treatments? Naturally acidic or alkaline lakes, that's a given. Lakes with short residence times, and this is when we're about less than 1 month over the growing season, not an annual average. It rains here a lot in Sweden in spring and fall. During the summer, there's no rain. Well, there's some, but residence time is a lot longer. Here we want to focus on external sources unless we're protecting downstream water bodies and the lake has high internal loading. Lakes with low alkalinity, even buffered forms of aluminum, will consume alkalinity and decrease pH. Dissolved organic matter can limit binding effectiveness, but aluminum still immobilizes phosphorus there. We can adjust the dose for this. I don't have time to talk about it. Other options are also generally affected, so DOM we just kind of have to deal with in most cases. Summary: aluminum forms a mineral that we find naturally in soils and sediment where it binds with phosphorus. Dosing has improved from guessing to immobilizing the mobile phosphorus pool, that phosphorus that can be released from the sediment and contribute to internal loading. Treatment methodology has led to improvements in binding efficiency and treatment effectiveness, and here we're talking both about split doses or modifying the amount added and how we add it. Benthic feeding fish can increase phosphorus binding or the binding efficiency of aluminum, but they also increase sediment mixing depth, so that's a net negative. Of course, benthic feeding fish can be accounted for or removed. Aluminum treatment is often the most inexpensive and effective treatment to reduce internal phosphorus loading, but like most measures, it's not effective or best for all lakes. There's no silver bullet that works everywhere. So I tried to list some cases here, but there's always going to be exceptions, and I'm not saying, aluminum it works, but maybe not for all lakes. Thanks for listening. Questions?
Okay, thank you very much, Brian, for another very nice talk here on aluminum-based treatments. So a question that we would have, in fact, from Heikki Mäkinen of the Vesijärvi Foundation here in Finland, concerning the estimation of the mobile phosphorus pool in the sediments, and specifically the depth horizon over which we should be considering this mobile phosphorus pool in estimating the dosing of the aluminum treatment. And Heikki is also referring to a study that we published from our group here into the sediments of Lake Vesijärvi here in Lahti, where we know that we have this type of deep reactive sediment layers that have accumulated in the 20th century, a very rapid sedimentation rate, high mobile phosphorus concentrations buried to great depth in the sediments. Do you have any experience of these kind of systems where, let's say, the mobile phosphorus pool might be somewhat larger than what you would predict from the uppermost few centimeters of the sediments? How would you approach a problem like this?
Yeah, that's a difficult one. You can do experiments to try and get a better handle on the active sediment depth. This Coleman Lake that I showed where we did the carp mixing study, it also had the same thing, untreated wastewater coming into the lake in the 60s, which led to a massive, basically bubble deeper in the sediment of mobile phosphorus. But it appeared in that case to be deep enough that it wasn't reacting with the water column. But we're really going to have to wait and see. And of course, carp are a compounding factor there. So, but that's tricky. I think you have to get a good handle on the active sediment depth in order to determine what depth you want to treat to.
Well, this involves, for example, studying the phosphorus concentrations in the pore fluids and this type of analyses that would allow us to see how what is the depth of the active layer.
That, and one simple way we do this is just to look at the profile of mobile phosphorus by sediment depth. And usually that stabilizes at some level. I mean, you can look at organic phosphorus too. That tends to go a bit deeper into the sediment before it stabilizes. But if you look at those two, you can get a decent idea of the sediment active layer, I guess, in a much simple way where you are sitting with data that you probably already have.
Okay, excellent, Brian. Thank you very much. And remember, please, Brian, join the discussion room in the online meeting at the end of the session. And all the participants who have additional questions, you can raise those to Brian during that session. So now it's time to move on. Thank you very much to Brian.